So, good morning. Today we have a lecture about synthesis and degradation of glucose. So it's quite easy lecture. I think that much of you know this topic, the glycolysis and gluconeogenesis from high school, yes? So, and for somebody, it can be also a new thing. So, before we start with the reactions, I will tell you something about the glucose, why we need glucose for our body, how the glucose is transported across the cell membranes, and how the glucose is phosphorylated and dephosphorylated. Yes? And then in the second part, we'll speak about glycolysis and gluconeogenesis. So, what's the role of glucose in the human metabolism? Glucose plays a central role in the saccharide metabolism. All saccharides that we eat can be transformed to glucose, and all saccharides can be produced from glucose. Yes? So, what monosaccharides we can have in diet? Fructose, for example. What else? Lactose, that's the disaccharide. And it consists of glucose and galactose. Yes? So, three main monosaccharides in diet are glucose, galactose, and fructose. And galactose and fructose can be easily converted to glucose. Also, in our metabolism, we have many different monosaccharides. Not only glucose, but also galactose, fructose, then, for example, pseudoheptulose or ribose. And all these monosaccharides can be produced in the body. Yes? About these reactions, it means how one monosaccharide can be converted to other monosaccharide. We will not speak today. You have special lecture about it, lecture about metabolism of fructose and galactose, and about pentose cycle. Yes? So today we will only focus on the role of glucose itself in the energy metabolism. So if we focus on the role of glucose in energy metabolism, it's a universal energy substrate for the body. All cells can use glucose as a source of energy. Yes? Some cells normally prefer other substrates, but all cells can use glucose if they need it. And also the glucose can be used in absence of oxygen. Yes? It's the only energy substrate that can be used in absence of oxygen. Yes? Only nutrient that can be used. Some tissues are strictly dependent on glucose. That are erythrocytes, for they have no mitochondria. And you can say that erythrocytes have anaerobic metabolism. Yes? It's a bit strange that erythrocytes that are carriers of oxygen have anaerobic metabolism, but it's true. Yes? For they do not have mitochondria, so they cannot use oxygen. And other tissue that can use only glucose are neurons in our central nervous system. They are strictly dependent on glucose, but there is exception that during very, very long starvation, they can use also ketone bodies. They can cover 50% of their energy expenditure by ketone bodies, and 50% they have to cover by glucose. Yes? So every day your brain consumes about 120 grams of glucose. During long starvation, about 60 grams. So even during long starvation, we need to produce glucose to feed these cells, erythrocytes and our neurons. Yes? What is it, glycemia? Everything what has suffix emia is the concentration of something in blood. So if it's glycemia, it's the concentration of glucose in blood. Yes? If you have natremia, it's the concentration of sodium in the blood. Yes? Kalemia, concentration of potassium in the blood. Calcemia, concentration of calcium. So glycemia, there's a concentration of glucose in the blood. This is the normal range. It's about 3.3 to 5.6. But it's important when you measure the glycemia. For glucose, that's a nutrient, so the level of glucose depends on what you think?
How much if we have eaten before?
Yes. If you have eaten before, and therefore is here written fasting level. Yes. For normally, if you want to measure glycemia, you have to do in the morning, about 7 or 8 o'clock. Yes. For then, all patients do not eat during the night normally. Yes. Problem is, for example, for rats. For rats are animals that eat only at night. Yes. So they have in the morning the highest glycemia. So for rats, you have to measure the glucose at different time. But for human beings, for we sleep at night, so we normally measure glucose, the glycemia in the morning, and also the patients should stop eating at about 6 o'clock the day before. Yes? But if you admit patient to the hospital, it can be also at 6 o'clock p.m., and you will measure the glucose, then you are not in this range, but the level should be below 7.1, yes, in the peripheral blood. So that's normal if the patient has 6.5 and he is after a meal, it's absolutely normal level, yes. But the lab will send you that it's higher, yes, but it's not true for the patient, it's not fasting, he's after a meal. Glycemia is very sensitively regulated. There are two groups of hormones that regulate. One increases, the second group decreases. The first group that is able to increase the glycemia, we call these hormones contra-regulatory hormones. And here you have the representatives. It's glucagon, epinephrine, or adrenaline, that is synonymous, growth hormone, and cortisol. Yes? This whole group is called contra-regulatory hormones. Yes? Why contra? For they fight against the other group, against insulin. Insulin is a hormone that decreases glycemia. And sometimes happens that patients do not have enough insulin. For example, when the patient has type 1 diabetes mellitus, he is missing beta pancreatic cells, he is missing insulin, and then there is no hormone that can decrease glycemia, and these patients have higher glycemia. That's called hyperglycemia. On the other hand, if you are missing these hormones, you have something that's called hypoglycemia. Yes, so the lower value of glucose than normal. Yes, so two other terms, hyperglycemia and hypoglycemia, higher or lower than normal. So this is for the beginning. Do you have any questions?
What is GH?
Growth hormone. Growth hormone, yes. There are four main hormones that increases glycemia, yes. But for example, growth hormones in different situations than epinephrine. For epinephrine, glucagon, cortisol, they are stress hormones. Growth hormone, that's not stress hormone. If we should continue, there are three main sources of glucose in our blood, yes. The first source is our diet, yes. In the diet, we accept every day hundreds of saccharides, 100 grams of saccharides, yes. So it's the main source of glucose for us. Other source of glucose is glycogen. There's a storage compound. It's a storage compound of glucose. And the third source of glucose is this pathway from pyruvate and other compounds to glucose that's called gluconeogenesis. Yes? So these are three main sources. If you look at this picture, if here in hour 0, you eat, for example, 200 grams of saccharides. So here you see, and then you stop eating, 200 grams and then nothing. Then you can see how long our body can live from these 200 saccharides, how long the body can live from the glycogen, and then how long it can live through the gluconeogenesis. So you see that 200 saccharides are used in about 5 hours, yes? Then from the third hour, when you do not eat something else, you start to degrade glycogen. The maximal value of degradation, the maximal rate of degradation is about 8 hours after the last meal. And at 16 hours, there is the crossing point, and from this time to the end is the main position of gluconeogenesis. Yes? So gluconeogenesis is important to survive long starvation. Glycogen is used especially to go through the short starvation. Yes? And if you know that, for example, we slept about 8 hours a day, then after the 8 hours we have some rate of gluconeogenesis yet. Yes? So even during night we have to start the gluconeogenesis. You know, I told to you that the glucose has the central position in the saccharide metabolism. It's not absolutely true, for the central position has its intermediate. Yes? The central position has the intermediate that's called glucose 6-phosphate. That's typical for almost all nutrients, that the nutrient itself isn't active. Yes? And it has to be activated something, and this is the crossing point. So for glucose, the active intermediate is glucose 6-phosphate. Yes? And therefore, every glucose that enters the cell is phosphorylated to glucose 6-phosphate. Yes? And then the cell can decide whether to store it, whether to transform it to other monosaccharides, or whether to degrade it to pyruvate in glycolysis. Yes? How can be compounds transported through the cell membrane? How you can transport compounds through the cell membrane?
Simple.
Yes. What else? There are 4 basic types how to transport all compounds, not only glucose. 4 types how to transport compounds through the cell membrane. Yes, so the pure diffusion, for example, for gases. Oxygen, carbon dioxide, urea goes by normal diffusion. I don't understand.
Membrane pores?
Yes, membrane pores, it means the membrane channels. So this is called facilitated diffusion. You have the pore in the membrane, a channel in the membrane, and according to the concentration gradient, the compound moves outside or inside. So there's the second type, by channels. Third type, active transport, yes, so you have to use energy to take some compound against the concentration gradient outside or inside. And the last, fourth.
Carriers?
Carrier, that's this. And this can be divided into symport and antiport, the third type. And the fourth type, if you have some huge compound, some big protein. Yes, so transport with the vesicles. Yes, outside or inside. So 4 basic types. Normal diffusion, passive diffusion, facilitated diffusion, transport with carriers or transport proteins, and then transport with vesicles. So what we will use to transport glucose? What of these 4 types? So do you think that the glucose can be transported by passive diffusion? No. Why not? There's no problem. Steroid hormones are bigger and they can go by normal diffusion.
Because it's polar.
Yes, it's polar. Yes. Glucose has no charge, but it's polar. And you know that the membrane is non-polar inside. So it cannot penetrate the membrane. So not passive diffusion. Can we use facilitated diffusion? Yes, we can. Active transport. We can use it. And transport of vesicles not. Yes, that's no meaning why to do it. So we will use the facilitated diffusion and the active transport to transport glucose. It's the same also for amino acids. Yes, it's the same for free fatty acids. 2 types, facilitated diffusion and active transport. We have two different mechanisms. The first is secondary active transport. Here is the abbreviation of the transporter. It's sodium glucose transporter 1 and 2. Sodium So there's the SGLT, sodium glucose transporter, 1 and 2. Number 1 is in enterocytes. Number 2 is in kidneys, in the tubular cells, in the proximal tubule. Yes? So that's the first way. Secondary active means what? Why not primary active? Why secondary active?
Supports an active transport in the other place of the cell.
Yes, so how it works?
With the epithelial cells or intestinal epithelial cells, we transport sodium into the cell, and on the other end we have to transport it out with the calcium from the pump.
Yes, very good. So it looks like this. Extracellular, intracellular space. Here we have the sodium glucose transporter. Glucose together with sodium go inside, yes? Both these compounds. Sodium along the concentration gradient, glucose against the concentration gradient. So the transport of sodium gives energy to transport the glucose. Yes, it's the horse that catch the glucose and take it to the cell. But on the different place, there has to be other transporter that returns this horse back outside the cell. Yes? And this other transporter is maintaining the concentration gradient for sodium. So this is NAK ATPase. Yes? This means secondary active. Primary active transport is if you use ATP at the place of transport. So you would have to use it here, but not here. Yes? Here we use the secondary active transport. What do you think is typical for these two organs, for our intestine and our kidneys? Why in these two tissues we have the same transporter? Do you have some similar function?
Absorption.
Yes, so they absorb glucose from outside our body. Yes, for intestine, yes, that's the inside. That's outside the body, yes. The same the kidneys. That's something, the tubules, that's something that is inside the body, outside the body, yes. Outside is not only our skin and so on, yes. So you can say that this transport is important to return the glucose back to the body, back to the circulation, yes. The second transporter, the GLUT transporter, it means only glucose transporter, only moves the glucose inside our body, yes, between one cell and other cell, between cell and plasma, between cell and interstitial fluid, yes. The second transporter is only the hole in the membrane, yes, it's a channel. If you open the channel, the glucose moves along its concentration gradient, yes? So no energy is used, but the problem is that you cannot concentrate glucose at one place, yes? This transporter is able to concentrate the glucose at one place and to produce big concentration gradient, this not. About the GLUT transporters, you should know that we have many types. Till now, we know about 7 basic types. In next 20 years, maybe other 20. We do not know. But you should remember these 4 transporters. 1, 2, 3, and 4. GLUT1 transporter, that's the transporter for cells that are strictly dependent on glucose. So it's in erythrocytes and in blood-brain barrier. Yes? Blood-brain barrier is what? What's blood-brain barrier?
That prevents the passage of noxious substances into the brain. It's usually composed of some microglial cells.
Yes. Yes, so it's the barrier between our brain, between our neurons, and our blood. Yes. It composed of endothelial cells and astrocytes. Yes. And the astrocytes has the GLUT1 transporter to take the glucose from the blood. GLUT2, it's a very common transporter. It's in liver, kidney, pancreatic beta cells, in enterocytes. GLUT3 is in the neurons. So this is in astrocytes, this is in neurons. And all these three transporters aren't dependent on insulin. Yes? This fourth transporter that's in adipose tissue, skeletal muscle, and in heart is insulin dependent. It means that without insulin, you do not have GLUT4 transporter in the membrane. And glucose cannot go into adipose tissue, into skeletal muscle, and into heart. With insulin, you incorporate the GLUT4 transporters to the membrane. And therefore, in books, you can also read that adipose tissue, skeletal muscle, and heart, they are insulin-dependent tissues. Yes? It means that they need insulin to use glucose as energy source. These three transporters, they do not need insulin. They are still in the membrane, and the cell can independently regulate their number in the membrane. For GLUT4 transporter, you need insulin. The more insulin you have, the more transporters. And the more glucose is used in these three types of cells. It's the first takes it from blood to astrocytes, and then from astrocytes to neurons. That's the GLUT3.
Yeah, but GLUT3.
GLUT3,
Brain.
it's brain, it's mean the neurons.
Between the neurons.
Not between astrocytes and neurons. Astrocyte is this, yes. For you have the blood-brain barrier is endothelial cells and astrocytes. And astrocytes are closely connected to neurons, but they have to exchange it through the interstitial fluid. So the astrocytes release the glucose, and the neuron takes it by GLUT3 transporter. You know, this list is not complete, yes? For there are many other cells where you have it, yes? You have also some GLUT1 transporter in liver, but it's not so common there, yes? And also in different books, you will read different things, yes? I put it together from more sources, and it's only for you important to know that we have some insulin dependent, insulin independent. From the insulin independent, you should know these three, and you should know this insulin dependent, yes? For this GLUT4 transporter is important in the pathogenesis of diabetes mellitus type 2. That's the diabetes mellitus if you are obese and you have many energy and you have also a lot of insulin. And then we are speaking about the insulin desensitization. For these cells become insensitive to glucose, yes? So even if you have a lot of insulin, these cells do not have enough GLUT4 transporter in the membrane. But during diabetes, the flow of glucose to these cells is absolutely normal. Only problem is here. So if we should close this topic, you have two types how to transport glucose: by secondary active transport, only to two cells, to enterocytes and to kidney cells. And the second is the facilitated diffusion. And there you have two basic types, insulin dependent and insulin independent. Yes? I've already said that when the glucose enters the cell, it has to be phosphorylated to the active glucose. That's glucose 6-phosphate. This reaction is important for the neutral glucose molecule is converted to the molecule with charge. The phosphate group has negative charge, yes? And this negative charge is important during the reactions. This one reaction, the phosphorylation of glucose, can be catalyzed by two isoenzymes. What does it mean, isoenzyme?
They're isomers to each other. They are genetically different, but their function is the same.
Yes, so they catalyze the same reaction, but they have different properties. For example, different amino acid composition. They can have different activators, different inhibitors. Their Michaelis constant can be different, yes? So they have different physicochemical properties. But they catalyze still the same reactions. And very often they are also in different tissues in our body, yes? One isoenzyme, for example, in erythrocytes, other enzyme in liver, third isoenzyme in kidneys, yes? And for phosphorylation of glucose, we have two isoenzymes, the glucokinase and hexokinase. This phosphorylation is irreversible. It means, the phosphorylation is that you take glucose, ATP, and you produce glucose 6-phosphate and ADP, yes? You cannot do the opposite reaction when you use glucose 6-phosphate together with ADP and you produce glucose and ATP, yes? All saccharides that have phosphate aren't macroergic, yes? So glucose 6-phosphate, it's not a macroergic compound. But, of course, that from glucose 6-phosphate you can produce glucose. But the reaction is catalyzed by phosphatase that can only remove the inorganic phosphate, yes? And it cannot incorporate it to ADP. Therefore, this reaction is irreversible, for you cannot take glucose 6-phosphate and ADP and produce glucose and ATP. Glucokinase and hexokinase. Glucokinase is in two organs. It's in our liver and then in pancreas, and in pancreas only in pancreatic beta cells. Glucokinase is active at higher glycemia. What means this? Km. What is it?
Michaelis constant.
Michaelis constant. What is it?
It's
Just the affinity of an enzyme.
Yeah, so it's affinity of enzyme to the substrate. And what means Michaelis constant 10 millimoles?
It's the concentration of substrate that makes the enzyme to function at its maximum speed.
Yes. So at a concentration of glucose 10 millimoles, the glucokinase reaches 50% of maximal velocity. Yes, that tells the Michaelis constant. So the higher Michaelis constant, the lower affinity for substrate. Why it's good to have so high Michaelis constant? For you know that the normal range is 3.3 to 5.6. So why our hepatocytes have the glucokinase? Here we have the graph where you can see this is the glucokinase, here we have hexokinase. And normal blood concentration is about here. Why in the liver? For you know that the liver do not meet the normal concentration of glucose. Yes. For after a meal, if you eat a lot of saccharides, they are absorbed in intestine, and the blood from intestine moves to the liver. Yes. And in this blood can be the concentration of glucose 20, 30. Yes. So there's not the normal blood concentration of glucose. The concentration in liver can be much, much higher. Yes. So if you know that in the blood from intestine is the concentration 20 to 30, so then you see that the glucokinase has quite high speed. Yes. And therefore in liver we have glucokinase. Yes. The more glucose you have, the faster the reaction is. And it's also important that the liver, in the normal concentration, it means during fasting, they do not use glucose. For you see that the glucokinase at normal blood glucose concentration is not very active. So during fasting, if you have in liver also only concentration, for example, 4, then the liver aren't able to use the glucose. Yes, quite effective. And the glucose can be used in other peripheral cells. Yes. So therefore, in liver, we have enzyme that has low affinity to glucose. Yes. This enzyme is able to use the glucose after a meal, and during fasting, it's not using the glucose. And why in pancreatic beta cells? The beta cells means the normal blood concentration. Yes. So it means somewhere here. But you see that here in the curve, the beta pancreatic cells can regulate their metabolism according to the concentration of glucose. Yes? For here, it's a linear. So here, it's, for example, 10% or 5% of the maximal velocity. And here, it's about 20%. Yes? So the beta pancreatic cells can modulate their metabolism according to the blood glucose concentration. Yes. Therefore, we have in beta pancreatic cells, we have also glucokinase. For here, the curve is linear, and they can react on the changes in the glycemia. In all other cells in our body, we have hexokinase. That's the enzyme that has Michaelis constant about 0.1. So you can see that very fast it reaches the maximal velocity. And in normal range, it has the maximal velocity. So our cells cannot modulate their metabolism by the concentration of glucose. Yes, according to the concentration of glucose. They have the maximal velocity from the beginning. Yes, concentration 0.1 you do not have, never. Yes, you are deaf if you have 0.1. Of course, that after that you can have it. Therefore, the hexokinase has to have other mechanism how it's regulated. The mechanism is that the product is inhibitor. So glucose 6-phosphate, the product of hexokinase, it's inhibitor. It means that if the cell takes the glucose, it phosphorylates it. And if the cell uses glucose 6-phosphate, then new glucose 6-phosphate is produced. Yes? But if there is somewhere inhibition in the metabolism and the cell stops, it cannot use the glucose, then you also inhibit the hexokinase and you produce no more the glucose 6-phosphate. Yes? So therefore, you can say that the hexokinase is dependent on the cell metabolism, how the cell is able to use the glucose. If the cell cannot use the glucose, for example, it's missing some enzyme, that also hexokinase is blocked. So this is the difference between these two enzymes, between hexokinase and glucokinase. And then the last, that's the enzyme important for the reverse reaction. It means to convert glucose 6-phosphate to glucose. The enzyme is called glucose 6-phosphatase. You know that phosphatase means that it takes phosphate from the molecule and it releases as inorganic phosphate. This enzyme is localized only in these 3 organs, in liver, in kidneys, and in enterocytes. In the cell, it's localized in the smooth endoplasmic reticulum. And to the smooth endoplasmic reticulum, the glucose 6-phosphate is transported by enzyme translocase. Why glucose 6-phosphatase in smooth endoplasmatic reticulum? For it's important, every glucose in the cytoplasm is phosphorylated. It doesn't matter whether by glucokinase or hexokinase. So if this enzyme is in cytosol and it produces glucose, then the hexokinase or glucokinase phosphorylated. And therefore, at the beginning, you have to take the glucose 6-phosphate to the smooth endoplasmic reticulum. Then you can use the glucose 6-phosphatase, you can remove the phosphate, and then from the smooth endoplasmic reticulum, you can release the glucose to the blood. But it cannot go back into the cytosol, for there it's phosphorylated. Yes? So this compartmentalization, you know that compartmentalization is one process, how the cell can modulate or regulate its metabolism. So here you see how it works. In smooth endoplasmic reticulum, you have dephosphorylation of glucose, and in the cytosol, you have phosphorylation of glucose. These organs are the only organs that can do the gluconeogenesis. Yes? Only liver, kidneys, and enterocytes can do gluconeogenesis, for they can produce pure glucose. Do you have any questions to this? Glycolysis can be defined as the reaction where you convert one molecule of glucose to 2 molecules of pyruvate or lactate. Pyruvate under aerobic conditions, lactate under anaerobic conditions. This reaction is localized in cytoplasm of all cells. Yes, all our cells have cytoplasm. All of them have enzymes for glycolysis. Of course, the glycolysis has many, many roles, but if we focus on the role in the energy metabolism, we can name 2 main roles. The first is, in glycolysis, you can produce energy. Yes? Inside the glycolysis, you have 2 reactions that can produce energy, that can produce ATP. How are called reactions that can produce ATP and not inside the respiratory chain? Substrate level phosphorylation. Yes? Phosphorylation at substrate level. And 2 of these reactions are in glycolysis. That's important for also without oxygen you can produce energy. Of course that with oxygen you can produce much, much more energy, but even without oxygen you can produce energy. The second role is that in glycolysis you can produce pyruvate. The pyruvate can be converted to acetyl coenzyme A, and acetyl coenzyme A can be used for synthesis of fatty acids. So glycolysis is also important for conversion of saccharides to lipids, yes, to triacylglycerols. That's the other role of the glycolysis. In the glycolysis, you can see 3 phases. The first is you have the glucose and you need to invest some energy. Yes? 2 ATPs per 1 molecule of glucose. You have to invest the energy to the molecule. In the second phase, you take the monosaccharide with 6 carbons and you cleave it to 2 molecules with 3 carbons. That's the second phase, catalyzed by aldolase. And then the longest phase, is the phase where you generate energy and you produce the end product, the pyruvate. Yes, so 3 phases. First, you need to give energy. Then you need to destroy the hexose molecule. And in the third phase, you take 3 carbon molecules and you gain energy from them and convert them to pyruvate or lactate. So here we have the scheme of of glycolysis. The first reaction you already know. That's the reaction when glucose is converted to glucose 6-phosphate. Yes? You use this ATP. Can you see it or not?
Yeah.
Yes? Glucose is converted to glucose 6-phosphate with the ADP, hexokinase, or glucokinase. In the second reaction, you do the isomeration. You take the glucose 6-phosphate and you produce isomer. Yes? So still the same the same number of carbon atoms, still the same number of hydrogen atoms, of oxygen atoms, only you change the something in the molecule. Here, you change glucose to fructose. You know that glucose is aldose, it has aldehyde group. Fructose has the keto group, yes? So in this reaction, catalyzed by isomerase, you change glucose 6-phosphate to fructose 6-phosphate. And here you produce the second tail, yes? You will use this first carbon atom in the next reaction when you let it react with other ATP. And you produce fructose 1,6-bisphosphate. This enzyme that's called phosphofructokinase, you have to remember, for it's the key regulatory enzyme of glycolysis. So this step, that's the key regulatory step in the glycolysis. Phosphofructokinase, conversion of fructose 6-phosphate to fructose 1,6-bisphosphate. This is the end of the first phase. Energy investment to the molecule. Now we have the second phase. In the second phase, you destroy these hexose and you produce 2 molecules with 3 carbon atoms. Reaction is catalyzed by aldolase and you produce glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. You know that these 2 molecules are also saccharides. Yes. We have 2 saccharides with 3 carbon atoms, glyceraldehyde and dihydroxyacetone. Yes? So still you have something that's saccharide. Only the smallest saccharides now you have. So glyceraldehyde 3-phosphate, dihydroxyacetone phosphate. The third phase begins only with glyceraldehyde 3-phosphate. Yes? So if you want to use also dihydroxyacetone phosphate, you need to convert it to glyceraldehyde 3-phosphate. Yes? To do this, there's also only isomeration. This is the ketose, this is aldose. So in this fifth reaction, you do the isomeration of dihydroxyacetone phosphate to glyceraldehyde 3-phosphate. Yes? So it's similar to this reaction between glucose 6-phosphate and fructose 6-phosphate. Here is the end of the second phase. So the destruction of the molecule and then the conversion of glyceraldehyde 3-phosphate, conversion of dihydroxyacetone phosphate to glyceraldehyde 3-phosphate. And these other reactions are the third phase. This sixth reaction is the most difficult reaction in the whole glycolysis. For you do 2 reactions at once. You take the glyceraldehyde 3-phosphate and you produce 1,3-bisphosphoglycerate. So you see that you have in the molecule 2 phosphates and also you do not have the aldehyde by glycerate, that's the salt of the carboxylic acid. And the reaction between aldehyde and carboxylic acid, that's oxidation. So in this one step, you do the oxidation and then the addition of inorganic phosphate. This aldehyde group on the first carbon atom is oxidated to the carboxy group. Yes? And on this carboxy group, you add the phosphate group. You take the inorganic phosphate from the cytosol and put it together with this carboxylic group. If you have one acid and other acid, and you have reaction between them, how it's called the bond between two acids. Anhydric bond, yes? And you know that anhydric bonds are macroergic, yes? The bonds in ATP, you have there two anhydric bonds, yes? All are macroergic. The same is here. So in this one reaction, you do oxidation, addition of phosphate, and you produce a macroergic compound, yes? And the compound is called 1,3-bisphosphoglycerate. The oxidation you do with NAD. You know that NAD is a cofactor of what? Of what types of enzymes? NAD, FAD, they are cofactors of oxidoreductases. Yes? They are cofactors of oxidoreductases. Here we use NAD. Yes? The other reaction is quite simple. You have macroergic compound, so you want to gain energy from it. So in this reaction, you only take this phosphate, this macroergic phosphate, and you incorporate it to ATP. So you convert 1,3-bisphosphoglycerate to 3-phosphoglycerate. Only you take the phosphate and you put it on ATP and you produce ATP. So first gain of energy. This is the substrate level phosphorylation. The reaction is also simple. You have 3-phosphoglycerate and you convert it to 2-phosphoglycerate. So you only change the position of the phosphate group. Here is the other difficult reaction in glycolysis. In this reaction, you remove water from the molecule. How it's called reaction where you eliminate water.
Condensation.
Not condensation if you let two molecules react together.
Dehydration?
Yes, dehydration, yes. So you take water from the molecule, and if you have elimination, you have to produce double bond, yes? So you take this hydroxy group, this hydrogen, you release this water, and you produce double bond. That's here. The enzyme is called enolase. What does it mean, enol? There's one type of compounds that have en and ol. How they are defined? Enols. The suffix ol means that they have hydroxy group, and the suffix en that they have double bond. If you put it together, enols are compounds that have double bond and hydroxy group bound to carbon with a double bond. Yes, so you have hydroxy group on double bond. And these compounds are unstable. Yes. For we have enol and we have keto form. We have enol form and keto form. And if you have both these compounds and you let them isomerase, more than 99% are in the keto form and less than 1% is in enol form. Yes? So this is other macroergic compound. This is the phosphoenol pyruvate. Here we have the phosphate, and this is the enol pyruvate. Yes? Here is double bond, and here is the hydroxy group that is used to form ester bond between acid and this hydroxy group. So we have enol, yes? Phosphoenol pyruvate. The last reaction of glycolysis is simply you only remove the phosphate. For this phosphate is able to stabilize the unstable enol pyruvate. If you remove this phosphate from the molecule. Then here you have isomerization in the molecule, and it isomerized to produce the keto form, the pyruvate. Here you have double bond here. Here you have keto group. Here it was enol group. Yes? And this isomerization from enol pyruvate to pyruvate, here you release the energy that can be used to gain the ATP. So therefore, this is the second substrate level phosphorylation reaction between phosphoenol pyruvate and pyruvate. In the test, you can have written, for example, the question that phosphoenol pyruvate has the macroergic bond between phosphate and enol pyruvate. Is it true or not? Is this bond macroergic? Not. Not. For this is normal ester bond. So this is hydroxy group and phosphate. So there is not the energy. The energy is in the isomerization of enol pyruvate to pyruvate. Yes? There you gain the energy. Here the energy was in the bond, in the anhydric bond. Here not. Yes? So therefore, very often in the test is question on this. Yes? How many intermediates in glycolysis are macroergic, for example? Yes? What type of macroergic bonds are in glycolysis? There is only this macroergic bond. This is not macroergic bond. Yes? So this was it. Do you have any questions? To this?
So the top one is macroergic because it's the anhydride bond?
Yes.
Okay.
And this is the ester bond, no energy inside. Also, this bond here, there is no energy. Yes?
Yeah.
There's the glucose 6-phosphate, it's not macroergic compound. This compound is macroergic, but due to the enol form is macroergic.
I said the first part of the third phase is investment, energy investment.
Yes.
Does it show numerically?
This is the ATP investment, this is the ATP investment. So 2 ATPs has to go to the reaction. And then here in the second reaction, you produce 2 ATPs per 1 triose. So altogether, you here gain 4 ATPs. Here you invest 2 ATPs, so 4 minus 2, it's 2 ATPs. So you produce 2 ATPs per 1 glycolysis. Yes?
Reactions 4 and 5 belong to the first one?
No, to the second. That's the second when you destroy the hexose and you convert the hydroxyacetylene phosphate to glyceraldehyde 3-phosphate. So now we ended with pyruvate. But sometimes you do not end with pyruvate, but you end with lactate. So when and why? Pyruvate, that's the branching point of glycolysis. Yes? You can stop here or you can continue. The fate of pyruvate depends on the concentration of oxygen in the cell. Yes? Important for you is that in the glycolysis you produce NADH, and this NADH has to be reoxidized somewhere. One possibility is in mitochondria, in the respiratory chain, or the other possibility is to put the hydrogen atoms to some substrate. Yes? If you have aerobic conditions, that the NADH is reoxidized in the respiratory chain. And then the pyruvate can be metabolized how it likes. For example, pyruvate can go to the matrix of mitochondria. There it can react with pyruvate dehydrogenase complex, and you produce acetyl coenzyme A from it. Yes? Or the pyruvate can be converted to alanine or to other things. So under aerobic conditions, you reoxidize NAD in respiratory chain, and the pyruvate's fate is in Krebs cycle or in transamination. Under anaerobic conditions, the problem is that you cannot reoxidize NADH in the respiratory chain. So you need to reoxidize the NADH by some substrate. And pyruvate is this substrate. The reaction is that you take pyruvate and NADH and you produce lactate. What's the difference between pyruvate and lactate? Do they have different functional groups, for example? Yes, hydrogen, so it means pyruvate has keto group and lactate has hydroxy group. Yes? So this reaction is reduction of pyruvate to lactate. So here, under anaerobic conditions, is pyruvate acceptor of electrons and hydrogen protons from NADH. The enzyme that catalyzes this reaction is called lactate dehydrogenase. Yes? This reaction is reversible. Yes? The ratio pyruvate and lactate is the same as the ratio NAD to NADH. Yes? And therefore, some analytical methods that wants to measure the oxidative state of the cell, they measure the concentration of lactate and the concentration of pyruvate. Then they compare these concentrations and they know the oxidation state of the cell. Yes? Whether the cell is missing oxygen or not. Yes? To measure these compounds, that's difficult. Yes? To measure lactate and pyruvate in the cell, that's easy. You know, this role of glycolysis, that was only the role in the energy metabolism. During the second year, you will learn that the glycolysis has many other important functions. Now I will show you one important function of glucose, of glycolysis, that is not coupled with energy metabolism. That's called 2,3-bisphosphoglycerate shunt. This is the normal glycolysis. You start with glucose, you have 1,3-bisphosphoglycerate, you have 3-phosphoglycerate, you produce ATP, and then you continue. Yes? In erythrocytes, some amount of glucose is used different. For you use this that's called 2,3-bisphosphoglycerate shunt. In this shunt, you take 1,3-bisphosphoglycerate and you do the isomerization to 2,3-bisphosphoglycerate. And then the 2,3-bisphosphoglycerate, you remove the phosphate from it and you produce 3-phosphoglycerate. Why erythrocyte uses this? For the 2,3-bisphosphoglycerate is the compound that can modulate the affinity of hemoglobin to oxygen. Yes? The more 2,3-bisphosphoglycerate, the lower affinity hemoglobin to oxygen. And for you know that in erythrocytes, you do not have many organelles, so it uses the glycolysis to use the shunt to modulate its affinity to oxygen. Yes? And the older the erythrocytes are, the more glucose is converted to this intermediate. Yes? Therefore, the older erythrocytes are worse in carrying of oxygen. So this is the one example how glycolysis can be used outside energy metabolism. This 2,3-bisphosphoglycerate channel.
Why do we want the affinity to go down?
You know, the erythrocytes has to sometimes, for example, during higher physical activity, it's better to have lower affinity to oxygen, for then it's easier to release the oxygen in the tissues. Yes? So the erythrocytes can regulate the affinity according to the body demands, you can say. Yes? of course, that if sometimes is the problems, for example, in blood transfusions, for then the erythrocytes in the blood transfusions are very, very old, and they have very high content of 2,3-bisphosphoglycerate, and it's not good, yes? So sometimes it makes this problem that when you have old erythrocytes, they can have a lot of 2,3-bisphosphoglycerate. About the regulation of glycolysis, you have 3 regulatory enzymes. All these regulatory enzymes catalyzes the irreversible reactions. But for you, it's only important to know the first one, the phosphofructokinase. Yes? That's the key regulatory enzyme of glycolysis. There are 4 main factors that modulate the activity of glycolysis. The first is very similar to regulation of Krebs cycle. You know that the rate of Krebs cycle is regulated by ATP and ADP. Yes? AMP is the same as ADP for you. The same, if you have a lot of energy in the cell, you block the glycolysis. If you have a lot of energy, there is no way why to produce the other energy. Yes? And you let the glucose 6-phosphate react to produce glycogen. Phosphofructokinase is inhibited by acidic pH. Why this?
Because of the phosphate group?
You know, the phosphate group still has something. It can be in the cytosol and in the molecule. Still, it's dissociated.
Is the active site destroyed?
Yes, that's the consequence. Yes, but why glycolysis is by acidic pH? You know, at the beginning of glycolysis, you have what? Glucose. Does it have some charge? No. Does it modulate the pH? Not. What's the end product of glycolysis? Pyruvate or lactate. So it means lactic acid or pyruvic acid. So from neutral molecule, you produce acids. So if you have very fast glycolysis, in the cell you produce a lot of acids. And if you have low pH, you destroy everything. So if you have low pH, you have to stop the glycolysis. Yes, for glycolysis is a very potent source of proteins. Citrate inhibits. About this we will speak in the lecture about the storage compounds in the body. This regulation is important in the state when you want to produce fatty acids from saccharides. Yes? For citrate that's produced in the Krebs cycle is the source of acetyl coenzyme A for fatty acid synthesis. Yes? And therefore, if you accumulate the citrate, it means that the rate of fatty acid synthesis is at the maximum level, and you don't want to produce new acetyl coenzyme A. Yes? But more about this regulation we will speak in the lecture about storage compounds. And then the last, there's the 4th factor. Glycolysis is modulated by hormones, by insulin and contrarregulatory hormones. Glycolysis is activated by insulin. It's the only catabolic reaction that's activated by insulin. Yes? And all other hormones inhibit the glycolysis. And this is the way how the hormones do it. Yes? They produce some compound that's called fructose 2,6-bisphosphate. Insulin produces more of fructose 6-phosphate, and thus it regulates the activity of phosphofructokinase. Yes? So this is connected together. Also, the insulin has other ways by second messengers how to regulate the metabolism, yes? But now remember this, yes? This is connected together. These are 3 independent factors. So, gluconeogenesis is a very simple reaction. It's the reverse reaction to glycolysis, but there are 3 exceptions, 3 different reactions. Gluconeogenesis is the synthesis of monosaccharides from non-saccharide compounds. And it's the only way how you can survive longer starvation for, if you remember the picture from the beginning of the lecture, 16 hours, that's the crossing point where you produce more energy from gluconeogenesis than from glycogenolysis, yes? And gluconeogenesis is activated also after the normal starvation in the night, yes? Here we have the precursors of gluconeogenesis. They have 3 or 4 carbon atoms, yes, the main precursors. Amino acids that they can have also more, of course. Here you have the main precursors. That's lactate, pyruvate, glycerol from triacylglycerols, and then amino acids, yes? Not all of them. You can use only these amino acids that are called glucogenic. 18 amino acids can produce glucose. So all amino acids except lysine and leucine. Yes? Those that begin with L cannot produce glucose. And one other compound that's important is, for example, propionate. That's the compound that can be produced from some strange fatty acids. Yes, you can produce propionate. I've already said that gluconeogenesis is only in organs that contain glucose 6-phosphatase. It means in liver, in kidneys, and in enterocytes. Only these 3 cells can produce glucose. And gluconeogenesis is localized not only in cytoplasm as glycolysis, but also in the matrix of mitochondria. Yes? The first different reaction is localized in mitochondria. You should learn this term for glycolysis and gluconeogenesis. They have the same reactions except 3 bypasses, bypass 1, bypass 2, and bypass 3. Yes? These reactions in gluconeogenesis, you have, instead of these irreversible reactions, yes? You know that hexokinase and glucokinase, they do phosphorylation of glucose, and it's irreversible reaction. So the third bypass will be the glucose 6-phosphatase. The same here. Phosphofructokinase takes fructose 6-phosphate and produce fructose 1,6-bisphosphate. To do the reverse reaction, you have to use the second bypass. And the last irreversible reaction, that was the conversion of phosphoenol pyruvate to pyruvate. And by the first bypass, you make the reverse reaction. Yes? So the bypasses, you have to do the reverse reactions to these irreversible reactions. Here we have the bypass 1. We will want the substrate, we will take pyruvate. Yes? So if you start with pyruvate and you want to produce glucose, in the first bypass, you need to do 2 reactions. The first is that the pyruvate has to be transported to mitochondria. Yes? Normally the pyruvate is in cytosol, so you transport it to mitochondria. And in mitochondria, it reacts with carbon dioxide. Yes? Here in form of bicarbonate. And you do the carboxylation. Carboxylation is the addition of carbon dioxide on the molecule. And you produce oxaloacetate. So the first bypass, first reaction, pyruvate to oxaloacetate, uses carbon dioxide, and you need ATP for this molecule. So 1 ATP is consumed. Then you take the oxaloacetate and you transport it to cytosol, back to cytosol. The way how to transport, you do not have to remember. Mainly, it's the reduction of oxaloacetate to malate. Malate has the transporter in the inner mitochondrial membrane. In cytosol, the oxaloacetate loses this group, yes? So in the first reaction, you put the carboxy group inside, and in the second reaction, you remove it back, yes? Also, you need a GTP, so macroallergic bond. Reaction is catalyzed by phosphoenol pyruvate carboxy kinase, and you produce phosphoenol pyruvate. Phosphoenol pyruvate, that's the intermediate of glycolysis. So from pyruvate, you produce phosphoenol pyruvate by these two reactions. That's the first bypass. The first is carboxylation of pyruvate, and in the second reaction is decarboxylation of oxaloacetate. Yes? It's a bit strange that in the first reaction you add the carboxy group, and in the second you remove it. Yes? But important for you is that you incorporate two macroallergic bonds in the oxaloacetate that can be then used to produce phosphoenol pyruvate. So this was the first enzyme. First bypass, and two macroallergic bonds are used. Here we have the second and the third bypass. They are much, much easier. Both of them only take phosphate from the molecule. So this was the first bypass. Here we have pyruvate, here phosphoenol pyruvate. Other steps are only reverse glycolysis. And here you have the second bypass. You have fructose 1,6-bisphosphate in glycolysis produced by phosphofructokinase. And in gluconeogenesis, you need to remove the phosphate. So you take phosphatase. It's called fructose 1,6-bisphosphatase. This is the substrate. Phosphatase remove the phosphate. That's the second bypass. And you produce fructose 6-phosphate. The next reaction is the same to glycolysis. Isomerization, fructose 6-phosphate to glucose 6-phosphate. And then you have the third bypass that you already know. That's the glucose 6-phosphatase. Yes? Takes the phosphate from the glucose 6-phosphate. So the only difficult thing on gluconeogenesis is the first bypass. Yes, two strange reactions. Other are simply. Gluconeogenesis consumes a lot of energy. Yes. Total, it consumes 6 macroallergic bonds in ATP. Yes. 2 are here. 1 in the first reaction, 1 in the second reaction, and 1 is here. Yes. So per 1 triose, you need 3 ATPs. You need 2 trioses to produce 1 glucose. So 2 times more, 6 ATPs. Yes? 2 of them in form of GTP. So here you see why only in liver, kidneys, and enterocytes you can do gluconeogenesis. For these organs are able to gain energy from other substrates, especially from fatty acids. So in liver, during starvation, they eat the fatty acids, they gain energy, and they invest this energy to gluconeogenesis. The same for kidneys. The cells in kidneys can use all energy substrates. So during starvation, they use fatty acids to gain energy, and they produce glucose. Yes? So the gluconeogenesis can be done only in those organs that have enough energy, that can use fatty acids. For you need a lot of energy for it. The substrates of gluconeogenesis, this picture you remember from the lecture about the overview of energy metabolism. Lactate, is one substrate of gluconeogenesis. The circle or the cycle is called Cori cycle. Yes? That's the cycle between red blood cells that produce lactate and liver that produce glucose. The second cycle that you remember, that's the glucose-alanine cycle. Yes? Pyruvate in form of alanine is a substrate for gluconeogenesis. Yes? About these sources, I have already said to you, all amino acids can be used, only leucine and lysine cannot be used. Yes? How it works, for that you have the lecture about the metabolism of amino acids. Yes? You can say that amino acids are converted to some intermediates of glycolysis or Krebs cycle, and from these intermediates you can produce glucose. How glycerol can be converted to glucose? There are two reactions. How to convert glycerol to intermediate of glycolysis. Yes? In the first reaction, you take glycerol, you do the phosphorylation of glycerol, and you produce glycerol 3-phosphate. And then in the second reaction, you convert glycerol 3-phosphate to dihydroxyacetone phosphate. Yes? That's only dehydrogenation. Glycerol has only hydroxy group. Dihydroxyacetone has one keto group. That's everything. So, do you have any questions? So then ask now or never. Good. Good. So look at this. Yes, for we will use it in other lectures about the lipids and especially about the storage compounds.